Next, we will discuss one of the fundamental ideas in precalculus, without which it will be impossible to formulate many calculus concepts. To understand the limits, we must understand the reason, that is, why do we need the limits, the notation, so that we can read and write the limit statements. We should know how to interpret the limit statements, and the purpose of the limits, that is, the type of tasks that we can perform using the limits. Let's start with the reason. Why do we need limits? Consider the following graph. Now imagine that you are talking to a blind person that doesn't know what the graph looks like. And let's try to describe the behavior of the function at the following locations. Let's focus on one, as the rest can be done in a similar way. In the past, I actually asked students to describe this behavior, and many of them struggled. So take a moment to think of how you would have described what happens to the graph of the function in the red circle. After a few drafts, we all can appreciate the following description. The output of the function approaches to 1 as the input gets closer and closer to -2 from the left. This description does a great job, but has the word count of 20. Wouldn't it be cool if there was an easier way to describe such behavior? Well, the limit notation does exactly that. The following statement in the language of limits communicates exactly the same information. Soon, we will learn how to concisely describe any behavior using the language of limits. And this is one of the main reasons for introducing the limits. They are very easy to use to describe the behavior of the functions. Now, let's discuss the notation. Every limit statement looks the same. There must be a function that is given in terms of some variable. The input variable must be approaching some target value, and the statement that we are making is that the limit is equal to something. Now, a function can be defined by a graph, an equation, or a table of values. The target value can be one of the following: a finite number or an infinity. And finally, the limit can be equal to one of the following: again, a finite number or an infinity, or it may not exist at all. Alternatively, we can use the following notation that omits the word limit and uses the arrow instead. For interpretation purposes, let's assume that the input variable is x. So how do we interpret the following limit statement? We say the limit of f of x as x approaches to its target value is something. Or we can change the order and say something is the limit of f of x as x approaches to its target value. Similarly, we can omit the word limit and say as x approaches to its target value, f of x approaches to something. Or we can change the order and say f of x approaches to something as x approaches to its target value. Initially, the main goal and the purpose of limits was to use the description of a function to make a limit statement, and vice versa, to learn something about the function from a given limit statement. But later, we will find other applications of the limits that go beyond just describing the behavior of functions. There are several ways to define and interpret the limits. I personally like to introduce the limits using the graphing approach, which is quite powerful when you have a graphing device. But when it comes to finding the limits and developing the supporting theory, we will discuss many other approaches, including numeric, analytic, epsilon-delta, and infinite arithmetic approach. We introduced the idea of a limit of a function and discussed the reason, the notation, how to interpret, and the purpose of the limits.